Hello, in a previous video we went over a solution to problem B5 from Putnam 1976. In this video I'm going to present a different solution to the same problem, and I came up with this solution after publishing that video, so I thought this was an interesting solution as well and you might want to see that. Okay, so here is the first part of the solution. The first part of the solution is we're going to plug in different values for n. If you plug in n equals 1 and you evaluate this sum, you're going to get 1. It's just going to be a constant 1. If you plug in n equals 2, you're going to end up with 2. N equals 3, you'll end up with 6. And n equals 4, you'll end up getting 24. Now, it's not very difficult to see the pattern here. These are all factorials. So 1 factorial, 2 factorial, 3 factorial, and 4 factorial. So what we're going to do is we're going to show that in fact this sum is equal to n factorial. Okay, so we claim the sum k equals 0 to n, negative 1 to the power of k, and choose k to the power of x minus k to the power of n is equal to n factorial. So here's what we're going to do. We're going to expand the binomial, so we get the sum k equals 0 to n, negative 1 to the power of k, and choose k. So this would be the sum, and choose j, x to the power of j, negative k to the power of n minus j, and j goes from 0 to n. Now I'm going to swap the two sums. So I'll have a double sum. I'm going to swap the two sums. So this is sum 0 to n, j 0 to n, sum k 0 to n. Then I'm going to first write down everything else in the sum. So negative 1 to the power of k, and choose k, and choose j, x to the j, negative k to the power of n minus j. Now I'm going to take out everything that does not depend on k, because the first sum, the inner sum, is independent of j. So I can take out anything that has j and n in there. So I have n choose j, that I can take that out. I have x to the power of j. So this term and this term do not have any k in there, so I can take those out. And I'm going to leave the rest in place, and I'm going to evaluate this inner sum. And choose k, negative k to the power of n minus j. Okay, so the negative 1 to the power of n minus j can be also taken out. So we get the sum j equals 0 to n, negative 1 to the power of n minus j, and choose j, x to the j. The sum k equals 0 to n, negative 1 to the power of k, and choose k to the power of n minus j. As soon as I got to this one, this reminded me of two things. Because of the plus minus sign here and the n choose k, it reminded me of principle of inclusion-exclusion, and k to the power of n minus j reminded me of the number of functions from a set to another set. So here is now what we're gonna do. So we will count the number of surjective functions f from 1 to all the way to n minus j to 1 to all the way to n in two ways. In every way, in the two ways that we are going to evaluate this one, we're going to get two different answers, and then we set those two equal. This is the method is called two-way counting method. Okay, so let's do that. One way would be this. If j equals 0, then you have functions from 1 through n to 1 through n, and that would be n factorial surjective function, because it's a set. It's from a set of n elements to another set of the same number of elements. So the number of surjective functions or onto functions would be n factorial. Then there are n factorial such functions. if j is positive, then n minus j is less than n. So the domain has less elements than the codomain. Therefore, there are no surjective functions. So the answer is 0 if j is positive, and if j is 0, the answer is n factorial. Now we are going to do that in a separate, using a separate method. Okay, so we're going to use PI, principle of inclusion-exclusion. So we will evaluate this using principle of inclusion-exclusion. So how do we evaluate that? We're going to look at first all of the functions. All of the functions would be, you have f of 1 could be any of these n elements, f of 2 could be also any of these n elements, f of n minus j could also be any of these n elements. So the number of functions is going to be n to the power of n minus j, since each f of x has n possible values. So f of 1 could be any of the numbers from 1 through n, f of 2 could be any of them, all the way to f of n minus j. So you have n to the power of n minus j. Now we are going to have to eliminate the ones that 1 is not in the range. So the number of functions where 1 is not in the range is, so we cannot choose 1. It would be n minus 1 to the power of n minus j. And this is true for 2 as well. So the number of functions where 2 is not in the range would be n minus 1 to the power of n minus j. And then we are going to have to look at the functions that 1 and 2 are not in the range of the function. So the number of functions where 1 and 2 are not in the range is n minus 2 to the power of n minus j. And you can just repeat that. So therefore, the number of surjective functions f from 1 through n minus j to 1 through n is, so the first one is n to the power of n minus j. We have to subtract the ones that 1 is not in the range, and we have to subtract the ones that 2 is also not in the range. So we have to subtract n of those. So that would be n choose 1, n minus 1 to the power of j minus 1. Then we have to add back the ones that 1 and 2 are not in the range, because the ones that 1 is not in the range has been subtracted once. The ones that 2 is not in the range has also been subtracted one more time. So we'll have to add back the ones that 2 of them are not in the range, and that would be, this is n minus j as the exponent, that would be n choose 2, and then minus n choose 3, n minus 3 to the power of n minus j, plus minus, etc. So this is the sum, negative 1 to the power of k, n choose k, n minus k to the power of n minus j, k equals 0 to n. It is not quite the same as what we had. Let's go back and take a look. What we had here was n choose k, k to the power of n minus j. However, n choose k and n choose n minus k are the same. So I can write this one down as k equals 0 to n. I'm going to replace k by n minus k. When I do that, n minus k also goes from 0 to n. Since when k is 0, n minus k is n. When k is n, n minus k is 0. So it would be negative 1 to the power of n minus k, n choose n minus k, n minus k, which is n minus n plus k, which is equal to the sum k equals 0 to n, negative 1 to the power of k. I'm going to take out the negative 1 to the power of n. N choose k, n choose n minus k and n choose k are the same, k to the power of n minus j. Okay, so by what we discussed before, this sum, negative 1 to the power of n, the sum k equals 0 to n, negative 1 to the power of k, n choose k, k to the power of n minus j. This is 0 if j is positive, and it is n factorial if j is 0. Therefore, the sum that they gave us, the sum k equals 0 to n, negative 1 to the power of k, n choose k, x minus k to the power of n is equal to. So I'm going to just take this one and plug it into what I had. This was the sum. If I go back and see what I had, and this is like a star. I'm gonna basically copy this down. Okay, let me write it down here. This is the sum j equals 0 to n, negative 1 to the power of n minus j, n choose j, negative 1 to the power of n minus j, n choose j, x to the j, the sum negative 1 to the power of k. If we just copy that down, n choose k, k to the power of n minus j, k equals 0 to n. Now this sum, we just saw that this sum is 0, almost always. This sum is 0. Except for when j is 0. So when j is 0, we get negative 1 to the power of n minus 0, n choose 0, x to the 0, and the sum they told, we found out that the sum is negative 1 to the power of n times n factorial. So this sum is negative 1 to the power of n times n factorial. So I'll just substitute that here, negative 1 to the power of n times n factorial. Now this is 1, this is 1, these two are 1, so that's just n factorial. And that finishes up the proof. So I like this proof because it uses the two-way counting, so it doesn't require really any algebra. I will put the link to the other video that includes the a different solution to this problem, and feel free to hit that and see the second solution to this problem. So if you enjoyed this video, make sure you subscribe to the channel and let me know what kinds of videos you like underneath this video, and I will see you in another video.